Hello everyone, this is Dr. Webb, and in this abstract algebra video we are going to be talking about cosets and a major theorem called Lagrange's theorem. So what are cosets? So we're going to start with a group, G, and we're going to take a subgroup of G, H. Then for any element A in G, we're going to be looking at the set, we're going to call it AH, and what this is it's A times all the elements of H. So A is being multiplied on the left. We're calling this the left coset of H in G containing A. So what a left coset is it is a subgroup where every element is being multiplied by some fixed element A. So we're thinking about A being fixed here and little h ranging through all the elements of big H. There's nothing special about multiplying A on the left. We can also multiply A on the right. And so we get what can be a different coset if this is a non-abelian group. Call it HA. And so this is all the elements, any element of H on the left and A on the right. And this is called a right coset of H. In fact, it's called the right coset of H in G containing A. Okay, so for these cosets, AH and HA, whether we're talking about a left coset or a right coset, A is called the coset representative. So it's sort of the element in G that is building the rest of the coset by multiplying it by the other elements of H. So one thing to note is that AH, this is always going to be a subset of G, because everything in H is inside of G, but AH is not going to be a subgroup unless A is already in H. It can't be a subgroup because it's not going to have the identity in it unless A is already in H. If A is already in H, then A inverse is in there, and so A times A inverse gives us the identity. But if A is not in H, then A inverse is not in H, so in particular we're not getting the identity, so there's no possible way for it to be a subgroup. So these cosets, these are different than subgroups. This is sort of it's a different type of thing than a subgroup. Okay. Well, what's important about these cosets is that these are actually building equivalence classes between elements of G. So what do we mean by this? So if we have A and B in G, and B is inside the coset AH, this means that B is equal to A times H for some H in H. Okay. Well, B being in AH, this is going to end up being equivalent to A being in BH. So let's prove this. So first of all, it's reflexive. So why is it reflexive? Well, since H is a subgroup, and so this means that the identity is inside H. And if the identity is inside H, this means that A times the identity is an element of AH, and A times the identity is A. Okay. So A is inside of its own coset. This is symmetric, so suppose B is an element of AH, and so as we see up here, this means that B is equal to A times H. Well, if we multiply both sides by H inverse, so we have B H inverse is going to be equal to A H inverse. And so HA inverse, this is just the identity. And so we end up with B times H inverse is equal to A. So this means that A is inside of the coset BH, because A, we've just written A as B times H inverse, and since H is in H inverse is in H as well. So A is inside BH because H inverse is inside H. So if B is inside AH, then A is inside BH. That proves symmetry. Because our A and B are arbitrary, this is proving the symmetry between them. Lastly, cosets are transitive. Being in a coset is transitive. So to prove this, let's suppose that B is inside AH and C is inside BH. Then what we want to show transitivity is that C is actually inside AH. So if B is inside AH, this means that B is equal to A times some H1 for some H1 in H. And if C is inside BH, this means that C is equal to B times H2 for some H2 in H. And so we have C is equal to BH2, but B is equal to AH1, H2. And so we have C is equal to A H1, H2. Since H is a subgroup, we have H1, H2 is an element of H. And so then this means that C is A times an element of H. So C is inside AH. And we've proven what we wanted to show. So, cosets, they are reflexive, they are symmetric, and they are transitive. Okay. And so what this means, if you recall that, recall about equivalence classes, is that if B is inside AH, then this means that the coset represented by A, so AH is equal to the coset represented by B, BH. And similarly, if C is not inside AH, that means that CH and AH can't share anything in common. They are totally disjoint. Now, in all of this, we've been proving this all for left cosets. The proof for right cosets is exactly the same. So same is true for right cosets. Okay. So these cosets set up equivalence classes of the group based on what coset you're in. And if we recall from talking about equivalence classes right at the beginning of the term, this means that these cosets actually give a partition of the group, depending on what coset elements fall into. Okay, so let's talk about the properties of cosets. So one thing we already saw before when we proved that this was reflexive is that A is inside its own coset. A is inside the coset AH. Similarly, A is inside the coset HA. So all of these, we're going to be writing these in terms of left cosets, but the analogous thing is true for right cosets. AH is equal to H if and only if A is inside of H. So I mentioned this before. If AH is equal to H, then that means that the identity is inside AH. And if the identity is inside AH, that means that A inverse had to have been in H. And if A inverse was in H, then A has to be in H as well. This is pretty obvious if you think about it. If you take AB, the coset generated by AB on H, then this is the same as taking A times the coset BH. The same thing's true with right cosets. Right? If you have something that's AB times an element of H, you can think about that as being A times B times an element of H. Really, this is just associativity in a sense. By the reflexivity, or by the symmetry, AH is equal to BH if and only if A is inside BH and B is inside AH. So this is what we proved when we proved that it was an equivalence relation. And same as we saw at the end of the equivalence relation, two cosets are either completely equal or they're completely disjoint. So they're equal, they either have everything exactly in common or they don't share a thing. Okay. So then we have, if AH equals BH, this is true if and only if A inverse B is inside H. So let's prove that this is true. So from what we saw earlier, if AH is equal to BH, this means that B is inside AH. And this means that there exists some H in H with B equal to AH. And then to complete this off, we're then just going to multiply the left of both sides of this by A inverse. And so we have A inverse B is equal to A inverse A times H, which is just H. And so this means A inverse B is an element of H. So for any two elements, A and B and G, the number of elements in AH is equal to the number of elements in BH. So this is true for any A and B and G. They don't have to be in the same coset with each other. And the reasoning here is that how many things are in AH? Well, AH is equal to A times H for all of the H in H. Well, when you multiply A by anything in H, you're going to be getting something different as you range through all those things in H. And so how many things are inside AH? It's exactly how many things are in H. Right? And it's just because if AH1 is equal to AH2, well, you could cancel the A's off on both sides. And so this only happens if H1 is equal to H2. Okay, and so when we multiply by all the different things in H, each time that you change your element H, you're going to be getting a new element in the group. And so the size of AH is equal to H. This is true for any A, and so this means that all of the cosets have exactly the same size, and that size is exactly the size of H. So lastly, this last one is kind of an interesting one, which we will see again in the future, although we won't be talking about it much more in this video. And it's that the left coset AH is equal to the right coset AH, if and only if H is equal to, so this is called a double coset, AHA inverse. Okay, so what does this mean? This does not mean that H is equal to a H inverse for any H in H. That is not what this means. Okay. What this means is if AH is equal to HA, this means that for any H in H, let's call it H1 in H, we have that AH1 is inside HA, and so that means that AH1 is equal to H2A for some H2. Well, H2 should be little. In H. And so then, let's see, how do we write this? This means that H1, A inverse is equal to H2. So H1 A inverse is inside H. This tells us that A inverse is inside of H. So to prove the other inequality, what we can do is, let's clear this out first. So we will take pencil H1 in H again, and so then we have that H1 is equal to H1 times A inverse, because A times A inverse is the identity, and since HA is equal to AH, I can write this as AH2 times A inverse, and so this is becoming from, since HA is equal to AH, H1A is inside AH, which means there exists some H2 in H, such that H1A is equal to AH2. And so we can conclude that since H1 is equal to AH2A inverse, that this is an element of AH inverse. And we are done. And proving the other direction is really pretty simple. Let's do that pretty straight through. So if H is equal to AHA inverse, then this means that for any H1 in H, H1 is equal to H2 A inverse for some H2 in H. And so then we have H1 A is equal to H2. So H1 A is inside AH, and since this is true for any H1 in H, this means that HA is inside, that HA is a subset of AH. On the other hand, using the equality on the other way, if H1 is in H, then H1 A inverse is going to equal some H3 in H, and so we have H1 is equal to H3A, and so AH1 is inside HA, and again, since H1 is just a general element, this means that AH is inside HA. And so these two together imply equality. AH is going to end up being a subgroup of G if and only if A is in H. And again, this boils down to, really this is coming from AH is a subgroup of G, implies that E is inside AH, the identity element. And again, the identity element is inside AH. This happens if and only if A inverse is inside H, which happens if and only if A is inside H. Okay. And so if it is a subgroup, then that means it has to contain the identity, and so A had to be inside H to begin with. So the only possibility that it has the identity is if A is inside H. And if A is inside H, then AH is just H. And from the beginning, we said it's a subgroup. Okay, this brings us to Lagrange's theorem, which really there's not very much we have to do to prove this. We've really done all the work already. And what Lagrange's theorem says is that if G is a finite group and H is a subgroup of G, then the order of H divides the order of G. Moreover, the number of left or right cosets of H and G is going to be equal to the order of G divided by the order of H. So the proof of this is very straightforward, and this is that the cosets of H are a partition of G because they are an equivalence relation. And so this means that there exist elements A1, A2, up to AN, such that we can write G as being the union of A1H, union A2H, all the way down to union ANH with these AIH being completely disjoint to AJH for any I not equal to J. Okay? And so then we have this now, this disjoint union forming G. And so this means that the size of G is equal to the size of A1H plus the size of A2H all the way down to the size of ANH. But all of these cosets are exactly the same size. They're all H big, and so this is just equal to N times the size of H. So G is equal to N, the number of different cosets we need, times the order of H, and this gives us our whole theorem. This encapsulates the whole theorem. So H divides G, the order of H divides G, and if I took the order of G and divided by the order of H, this is going to give me N, where N is coming from the number of coset representatives. So this is number of different coset reps needed. Okay. And so this number of different distinct cosets needed, this has a special name. It's called the index. And so the index of G and H is written brackets G colon H. And so one way to think about what Lagrange's theorem says is that the order of G is equal to the index of G inside H times the order of H. And this is if the order of G is finite. Okay. So if G is finite, by Lagrange's theorem, we have the index, the number of different distinct cosets, is equal to the order of G divided by the order of H. If G is infinite, then there's no nice Lagrange's theorem because G is infinite. And so you can have infinite cosets, or you could have infinite subgroups or finite subgroups. But even if G is infinite, even if G has an infinite many number of elements, it is still possible for subgroups to have finite index. And so it's still possible for there only to be a finite number of distinct left or right cosets of H inside of G. And so sometimes, if we're dealing with an infinite group, sometimes it's important to focus in on the subgroups that have finite index. And so this is, when we say finite index, this is what we're talking about. That when we partition G by H, using either left or right cosets, there's only a finite number of them. So that is all for this video. I will see you again soon.